All right, so we are talking the Gibbs Sampler. It's an important MCMC method, right? So, big picture, what are we doing with the Gibbs Sampler? So the goal is to get a sample from a target multivariate distribution. I guess multivariate joint distribution. And the idea is maybe the joint distribution for all the variables, maybe that's complicated and difficult for us to sample directly from, right? So probably, joint distribution of all variables is difficult to sample from directly. So what does the Gibbs sampler do? Is it breaks down the joint distribution that breaks down the joint distribution into multiple univariate conditional distributions. Okay, that are straightforward to sample from. Okay, so instead of trying to sample from some complex joint distribution, we break it down into a bunch of univariate conditional distributions. Okay. All right, so I'll do an example with a discrete distribution, which is silly because it's very easy to sample directly from a multivariate discrete distribution. But we'll this is just for illustration. Okay, so for illustration, we will do Gibbs sampling on a multivariate discrete distribution. Okay, and this would never done in real life because it is easy to sample directly. Okay, to sample directly from such a distribution. All right, so let's so this is a silly example, but let's say there are three states to consider. We've got California, Colorado, Texas, and we'll say, do you drive a car or a truck? Cars and trucks. Okay, so the total joint distribution will sum up to 1, and we'll say California is 0.4, Colorado is 0.25, and Texas is 0.35. And then we'll do 0.1 and 0.3. I don't know. we'll do this. I'm just making up numbers, okay? Okay, so this is the joint distribution. Okay, and again, in real life, it's very easy to sample from the joint distribution directly. But we are going to do Gibbs sampling, okay, which we would not do in real life. But for illustration, we can kind of illustrate the concept of starting at some point and then drawing from univariate conditional distributions. Okay, so let's say our initial point is California cars. Okay, so maybe I'll do initial point is, so we'll say the state is x1 and the vehicle is x2. So the initial point is x1 equals California and x2 equals cars. Okay. So we draw the next value of x1 from the conditional distribution of x1 where x2 is equal to cars. So we will draw x1 at time, so this is x1 at time 0 and x2 at time 0. We'll draw x1 at time 1 comes from the distribution of x1 given that x2 is equal to x2 at time 0, which is cars. Okay, so if we condition on cars, then we have x1 at time 1 coming from the distribution that California has probability 0.3 divided by 0.6, or which is equal to 0.5. Colorado has probability 0.15 over 0.6, which is 0.25, and Texas has probability 0.15 over 0.6, also 0.25. Okay, so x1 will come from this univariate distribution where California has probability 0.5, Colorado has probability 0.25, and Texas has probability 0.25. Does that make sense? Okay, and so you just randomly draw from this univariate distribution, and let's say we draw Texas. Okay, so x1 at time 1 will be Texas. Okay, so far so good. Let me just copy this. Oops. Copy your joint distribution. Okay, so we have x1 at time 1 is equal to Texas. So now we draw x2 at time 1 from the conditional distribution of x2 given that x1 is equal to x1 at time 1, which is Texas. So we have the x2 at time 1 comes from the distribution of x2 given that x1 is equal to Texas. And so x2 comes from the distribution of cars, which has probability 0.15 over 0.35, so that's 3 out of 7. And trucks, has probability 0.2 over 0.35 has probability 4/7. So x2 gets drawn from here. So let's say we randomly draw trucks. Okay, so x2 at time 1 equals trucks. So the coordinate x1 at time 1 and x2 at time 1, also at time 1, will be equal to Texas and trucks. So we'll draw that. Okay, and then at the next iteration, what do? We draw x1 at time 2 coming from the distribution of x1 given that x2 is equal to trucks, which is going to be California has probability 0.25, Colorado has probability 0.25, and Texas has probability 0.5. Okay, and then we draw x2 at time 2 from probability of x1, probability of x2, given that x1 is equal to whatever we drew at the last thing. So let's say, we draw x2 at time 2 being Texas again. So then this will just be the distribution of x2 given that x1 is Texas, and that's going to be cars with probability 3/7 and trucks with probability 4/7. Okay, and we draw from this distribution. Maybe we draw cars, or maybe we draw trucks or something. Okay, it doesn't matter. You just keep iterating back and forth using whatever your most recent value to condition the other distribution. Does this make sense? So this is to kind of illustrate the idea of conditioning on one variable, okay? And then, with a two-way table, conditioning on one variable means you're just looking at the column only, or you're looking at the row only after you set it equal to something, after you make condition there. All right, is that good? Okay, so let's take a look at kind of a slightly more realistic example, and we'll look at Gibbs sampling for a bivariate normal distribution. So this you will do this in your homework. And so I've actually posted homework 5. That's up on CCLE under week 9. Okay, and I think it's an easy homework, but I don't know. Maybe it's not. There's only 3 problems. Okay, the first one is use the deciphering code. I've given you some secret messages, and you try to decipher them. And I think it's kind of fun. And then. My idea of fun. And then the other 2 is, one you're going to do Metropolis algorithm for a bivariate normal, and then you'll do Gibbs sampling for bivariate normal. Okay, and you'll kind of see a little bit of the difference between the 2. Which, we'll see. Okay, so Gibbs sampling for bivariate normal distribution. Okay, so our target distribution, will be normal distribution with mean vector equal to 0, 0, and variance covariance matrix 1, row, row 1. Okay, and so the multivariate normal PDF its PDF is technically the determinant of 2 pi sigma to the negative 1/2 e to the negative 1/2 x minus mu transpose inverse sigma x minus mu. So there you go. Okay, and then if we look at the determinant, it's going to be 1 minus rho squared, and when you throw this part becomes 1 over 2 pi root 1 minus rho squared, and then sigma inverse itself is going to be 1 over 1 minus rho squared times the matrix 1 minus negative rho 1, and then you'll have your x vector x1 minus x2, or not minus, x1 x2 transpose times x1 x2, right? So you have all of this matrix multiplication, and you have exp to the 1/2 of all of this. Okay, and so when you simplify all of that, we end up getting our PDF, P of x1 and x2 is going to be equal to 1 over 2 pi times root 1 minus rho squared of e to the negative, and this ends up being x1 squared minus 2 rho x1 x2 plus x2 squared over 2 times 1 minus rho squared. All right, so that's going to be our target PDF. Okay, and for Gibbs sampling, we will draw x1 at time t from the distribution of x1 given x2 set equal to x2 at time, I guess, t minus 1. And we'll draw x2 at time t from the conditional distribution of x2 set given where x1 is equal to the value we just drew. Okay, so we need to find basically the probability of x1 given x2 and probability of x2 given x1. So is there like a bird in here? Or are they just really loud outside? I don't know. Okay. All right, so this, just using the definition, is going to be our joint distribution divided by the univariate distribution of x2. Okay. Now keep in mind, so we are treating x2 as a constant. Okay, x2 is being set equal to the value, the constant value of x2 at time t minus 1. Okay, so we're treating x2 as a constant. Okay, and anyway, well, before we even treat x2 as a constant, well, the probability of x2 itself is going to be the integral of the joint distribution, x1 and x2, where we have considered every single possible value of x1. Okay, and if we consider the joint distribution across every single value of x1, we get this, and this is a constant. This becomes a constant when x2 is set equal to the constant value x2 at time t minus 1. Okay. So all to say is that x1 given x2 is just proportional to the joint distribution. Okay, so the conditional distribution is proportional to the joint distribution when we set x2 equal to a constant. Okay, great. Well, let's keep working here. So we've got x1 given x2 is proportional to the joint distribution of x1 and x2 when x2 is set to a constant. Here is the PDF of that joint distribution. Okay, so that's what we have. This part over here, this is just a constant. Okay, and also, so I'll just say it's proportional to exp of, and I've got minus x squared minus 2 rho x1 x2 divided by 2 times 1 minus rho squared. And because it's e raised to a thing, I can take out this part, the x2 squared times 2 minus 1 minus rho squared, right? Because here I'm just adding it, and it's just, you multiply the exponents. So when you get e raised to a sum, you can kind of split them up into a product, and then thus this term is a constant when x2 is a constant, which is the case. So this term is a constant when x2 is a constant. So it just becomes proportional to this piece right here. So now I just have exp of negative x squared minus 2 rho x1 x2 over 2 times 1 minus rho squared. So far so good? Okay. This thing sorry, it's not minus, it's minus the entire thing here. Okay, I'm going to complete the square here. So I've got minus 2 rho x1 plus rho squared x2 squared minus rho squared x2 squared. So I'm doing that. So these are equivalent. Okay, and so down here, well, I can leave it equivalent. And so we've got exp of minus, and here I'm going to have x minus x1, sorry, x1 row squared, no, not row squared, row x2 quantity squared over 2 times 1 minus row squared. And then this part is just another constant being multiplied right here, right? It's going to be negative negative row squared x2 squared over 2 times 1 minus row squared here. But this part's just a constant, so we can throw it away. Okay. So this is proportional to e of minus x1 minus row x2 squared over 2 times 1 minus row squared. Does this look familiar? No. All right. Is all the math I've done so far okay? All right. So and we're okay with just like I don't know what's the right word, factoring this out and then just throwing it away because it's a constant, because we're treating x2 as a constant throughout the thing, right? So we treat x2 as a constant because it is. X2 is set to the value x2 at time t minus 1. Okay, so anyway, so we have x1 given x2 is proportional to this thing right here. And okay, well, if we look at oh, let me close this up. Normal distribution. Here's the PDF for the normal distribution. Okay, so this is a normal PDF. We have, okay, so we've got a constant, so we don't have to worry about that. But what do we have? We've got x1, so this is going to be, let mu equal what? Row x2. Okay, and then we've got the numerator there. And what do we set sigma squared to be? 1 minus row squared, exactly. Okay. So so this is going to be proportional to the normal PDF of variable x1 with mu equal to row x2 and sigma squared equal to 1 minus row squared. Okay, so that's what we have. So we got the conditional distribution of x1 given x2. Given x2 is equal to the normal distribution with mu equal to row x2, sigma squared equal to 1 minus row squared. Great. Okay, and then by symmetry, or you could even do the math yourself, we will get x2 given x1 is equal to normal with mu set equal to rho x1 and sigma squared equal to 1 minus rho squared. Okay, sound good? All right, so this will be the Gibbs Sampler, I guess the systematic Gibbs Sampler for a bivariate normal with target, distribution normal to mu equal to 0, 0, sigma matrix 1 minus 1, rho, rho, 1. Okay. So we'll say let our coordinate x at time t be x1 at time t and x2 at time t. Okay, so then we will generate x at time t plus 1 being x1 at time t plus 1 and x2 at time t plus 1. What we will do is we will get x1 at time t plus 1 coming from conditioned on x2 at time t. This will come from univariate normal with rho with mean x2 at time t and variance 1 minus rho squared, and x2 at time t plus 1 conditioned on the value of x1 that we just drew will be we'll have a normal distribution with mean set to rho times the x1 value that we just drew and variance 1 minus rho squared. Okay, and you would just continue iterating between each step. And so you'll be coding this up in your homework this week. So you have pretty much everything you need, and in the homework you'll code this up. So yes, I recognize that in R there is a package that allows you to draw samples directly from the multivariate normal. We'll pretend that doesn't exist, otherwise this becomes a trivial problem, right? So what we're going to do is we're going to run Gibbs sampling, and we're going to say, well, we can't draw from the multivariate normal directly, but we are able to draw from univariate random normals. So for the problem, you are allowed to use R norm, because we're going to say you are able to draw from the univariate normal distribution. So you'll draw from R norm, and then you'll run the chain. And you'll condition your R norm based on x1, and then once you get that value, you'll condition your R norm on x2, and then you'll draw new value, and then you condition it, and you keep cycling just between the two. And it should be pretty straightforward, and your resulting chain should look like a bivariate normal distribution. Okay, and just like the other things, you can start off with a terrible starting location, and it will seek out correct versions, okay, or correct values. So it will work. Okay, are there any questions here? there's a little, like, I'm not going to do the induction proof, but by induction, we can show that at any time t, x1 at time t and x2 at time t, this will come from a bivariate normal. And if you kind of continue building up, you'll have rho raised to the t to the 2 times t minus 1 times, so if you start off at x2, if you condition on x2 at time 0, then your next iteration will be, so if we just flip back a slide, so the next iteration the next iteration will be rho times x2 at time t, okay? And so if you carry this on, week 8, Friday, okay? So so each iteration you go through, you start off at x2, and then the next one will be whatever value you drew there, you do it again. And so the first time it's going to be rho times x2, and then so if t is 1, it'll be rho times x2, and then we've got rho at times kind of t squared, t times 2, rho squared times x2, because first it was conditioned on x0, and then we multiplied by rho, and then at the next value it's conditioned there, and so it becomes rho times that, so it becomes rho squared times x0, or x at time 0, and then the next time we multiply by another rho, so it's like rho cubed, and so on and so forth. So it continues on, and so we're continuing to multiply by all of these rows, and then and likewise, I didn't do the math here. I'm actually not even showing the math at all. Is this going to be 4t minus 2 rho minus rho 4t minus 1, and here I got rho minus rho to the 4t minus 1, and down here I got 1 minus rho to the 4t. Okay, all this to show is that as t approaches to infinity, okay, and rho is less than 1, these things, as they get larger, as t goes to infinity, these things will go to 0, right? This becomes 0 and 0, and all of these things become zeros, and so we get 1 minus 0, rho minus 0, rho minus 0, and 1 minus 0, okay, which is our target distribution. So as t goes to infinity, x1, your x vector at time t draws from the target distribution. Okay. Is it all right? All right. That's all I have for today. Next week, we'll start looking at hierarchical models, which are really cool, okay? And Gibbs sampling works very well with hierarchical models. And we'll talk through that, and we'll look at some, I don't know, kind of a neat application there. All right, have a good weekend. No class on Monday. It's Memorial Day. We remember fallen soldiers. And so we'll see you guys on Wednesday. Have a good weekend.